Section 7. Block signing. Unlike the Bitcoin network, the process of block creation within Elements is not reliant on proof of work. Instead, Elements uses a strong federation of signatories, called block signers, who sign and create blocks in a reliable and timely manner. This removes the transaction latency inherent in the proof of work mining process, which is subject to large block time variance. The federated block signing process achieves reliable block creation without introducing the need for third-party trust. So far, throughout this tutorial series, we have been using the generate command to create blocks, which ignores the block signing model in order to make development and testing easier. In this section, you'll learn how to set up an Elements node to support a federated signing model. This will allow you to specify the number of signatures required in order to produce a valid block. We'll be setting up our nodes to require 2 of 2 multisig block creation. This will be set up using the sign block script parameter, which can be added to the Elements config file or passed into the node on startup. In order to initialize a chain with this parameter, we first need to build the script that it's made up of. We'll do this using some existing nodes, save the data they output, and then wipe the chain so that we can restart it using our sign block script parameter. Now, this is necessary as the script forms part of the network's consensus rules and will need to be set on chain initialization. This script cannot be added at a later date to an already existing chain. So, since we've already started this chain that we have running right now, we'll have to generate the sign block script, clear all the chain's data, and then restart it by passing in this new sign block script. All right, let's go ahead and do just that. First, we'll need access to 2 Elements nodes, which we'll call E1 and E2. This setup is the same as in the previous tutorials. The nodes have had their blockchains reset and the default assets split between them. So, just to illustrate that, first of all, let's recall that we have 2 nodes here running. One is called E1, which we can query using E1 CLI. And we also have one called E2, which we can query using E2 CLI. Perfect. Now let's go ahead and look at E1's elements.conf file. Please note here that this option, con max block sig size, has been set to 2000. And this is actually the case for E2's element.conf as well. And this is necessary just for later on in this tutorial. If you don't have the maximum block signature size set, then the 2 of 2 multi-signature will be too big and the blocks will not be valid. So, just make sure you have that set. All right. Since we will be resetting the blockchain and wiping the wallets associated with E1 and E2, we will need to take a copy of the addresses, public keys, and private keys that we use to generate the block signing script so that we can use them later. So first, what we need from each node is to generate a new address. All right. Let me go ahead and do that using the E1 CLI get new address command. Before I run this, I'm just going to clear the terminal so that we have a fresh start here. E1 CLI get new address. And we see this produces an address. And similarly, we can run E2 CLI, get new address, and this produces a different address. And we can actually see that they are different because they end with a different strings of characters. All right. What we need to do next is extract the public keys from these addresses. We can do this from E1's address by first copying the address and then running E1 CLI get address info and then passing in that address. And here we have a big data dump, and right here we can see the public key of this address. Next, we can run the same thing for E2 CLI. So E2 CLI get address info, and we can just copy E2's address and pass that in. And right here, we can see the public key for E2's address. One more piece of information we'll need from each node is the associated private key with each address. We can derive this, we can grab this from the address very simply with the dump priv key RPC. So if we run this on E1's address, we will get the associated private key. And similarly, if we just get the command we ran to get the public key for E2, we can just swap this get address info RPC with the dump priv key one. And right here, we will see the associated private key for E2's address. All right, let's keep all this output here because we're going to be needing it soon. Next up, we're going to want to create a redeem script with a 2 of 2 multi-signature. We can do this by using the simply named create multisig command. So that's E1 CLI create multisig. All right. So this first argument we're passing in is the number of signatures we want to satisfy for the script. So since this is a 2 of 2 script, we're going to need 2 valid signatures. So let's pass 2 in there. And next, we need to pass in a list, a quoted list here, of what we're going to want here is E1's public key and E2's public key. So this is going to be the actual list of public keys whose signatures we're going to need. And we're going to actually need 2 of these signatures. So let's go ahead and grab E1's public key from the above terminal output and pass that in here. And similarly, we can pass E2's public key for that address right here. And let's go ahead and run that. Oops, forgot to close off this quotation mark. Let's run that again. Perfect. So this gives us a redeem script that is a 2 of 2 multisig. Before proceeding, let's just review what we've done. We've launched, before this tutorial, I launched a elements reg test chain. From there, we have 2 nodes. In each of them, we generated an address, and from that address, we got a public key and a private key for each node. And these public and private keys are what we're using for the multisig. So we generated this multisig, which is a 2 of 2, and this means that we need a signature from both of the public keys we passed in order to satisfy these scripts. What we're going to do now is actually copy this redeem script. Next, let's wipe the existing blockchain and wallet data so that we can start the blockchain again, but this time with the criteria for signing blocks set as this redeem script. So we can do this by first stopping both of the nodes, E1 CLI stop and E2 CLI stop. Now I'm going to completely remove the data of both of these nodes have about the blockchain. So I can do that by getting the first node's data directory and deleting the elements reg test directory. And let me do the same thing for the second node's data directory. Perfect. Now I have, in essence, deleted the previous blockchain, but we still have this redeem script saved. So let me go ahead and run E1 DAE, which is the alias I have set up to start the first elements node. And what I'll do is I will pass in a sign block script argument here. This option tells elements, hey, let's set this sign block script of this new chain equal to this 2 of 2 multisig redeem script, which we've entered. So one more thing we're going to have to pass in is this EVB params equals dynafed : 0, : By default, elements will launch a new chain with dynafed activated. We don't want dynafed. We don't want that active here because that will really complicate block creation. You're welcome to activate dynamic federations, also known as dynafed, in your own elements chains. But for now, for this tutorial, let's add in this setting here, which will disable dynafed and make everything else a lot easier. So let's go ahead and run that and launch E1. Perfect. E1 has started. And now we can run the exact same command and simply launch E2. So let's do that as well. Perfect. Now we have both of these nodes running on this new chain that we've created, because recall, we wiped the data from the previous blockchain. We have these two nodes running, and they are both aware that the sign block script, the criteria to create a block, is this 2 of 2 multi-signature script. All right, now let's go ahead and try to actually generate a block how we used to in the previous tutorials using the generate command. We can do this with E1 CLI generate and pass in 1 just to generate one block. And actually this doesn't work because since we wiped the chain, we need a wallet. So let me go ahead and I actually did forget to do this. Let me create a wallet for E1. We can just give it an empty name. And let's run the same command on E2. So now E1 and E2 both have wallets. Now let's rerun that generate command. And what we can see is it says blocks is null. So no blocks were created. And that's because in order to create a block on this new chain, we need this sign block script satisfied. So let's go ahead and do that. Let's create a new block using E1 CLI get new block hex. And actually, before proceeding, let me just clarify why this didn't work, just to make sure we're all on the same page before proceeding. Both E1 and E2, since we passed in this sign block script argument, are enforcing the rule themselves that any block they accept must have this script satisfied. All right, let's go ahead and try to satisfy the script. So if we run E1 CLI get new block hex, we get this new block, the hex of it actually, as per the name. But just remember that this command only creates a block that we can now propose to all the nodes and try to get them to sign. It doesn't actually generate one. And we can confirm this by running E1 CLI get block count. We'll see that this count is 0. So this get new block hex RPC did not actually submit this new block. It simply created one. Let's go ahead and copy that block hex. And you know what? Let's actually try and submit that just to see what's going to happen. And we can see we get the error block proof invalid. All right, so it sounds like we actually need both nodes to sign this. All right, so it sounds like we actually need both signatures on the block before we can submit it. So let's go ahead and actually generate those signatures. First, however, we're going to need to import those private keys into E1 and E2, which we generated earlier. Because remember, we cleared all the blockchain data, so now, and we made new wallets, right? So now these two wallets are not aware of the previous keys, but we can make them aware by importing those keys. So we can do this by running E1 CLI import priv key. And let's scroll all the way up here and go ahead and copy that address from E1's associated private key. And let's paste that in here. And let's do the same thing for E2. So E2 import priv key. We can copy that private key we dumped earlier from all the way over here and paste that in. Perfect. Now we should actually be able to sign this block, which we created with the get new block hex RPC. Let's run E1 CLI sign block. So this RPC is called sign block. And just sign the block. Pass in the block hex. And here we get this output. This is the public key, which was used to sign the block. And this is the associated signature. And if you're running this on your own, make sure to confirm that this public key is equal to that public key, which we grabbed earlier from E1's address. Now let's go ahead and actually run the same command on E2. So E2 CLI sign block and pass in that block hex. Perfect. Now we have these two signatures. We need to combine them together. So there is another RPC named combine block sigs. And this will allow us to combine this block's signatures. So let me go ahead and run that with E1 CLI combine block sigs. And before I run it, let's just run it with no arguments to see the documentation. And we can see what it expects is one argument, which is the block hex, which of course we already have here. And the second argument is a list of these pub key sig pairs. Now, if we look, that's actually what that previous signed block RPC outputted. So we have these pub key sig pairs from both E1 and E2. So it sounds like we have all the information we need to run this. There's also a third optional argument called witness script. We only need this one if Dynafed is activated. And if you'll recall, previously I told you to pass in, let's just scroll up here. When we started up this new chain, we passed in this argument which disabled Dynafed for our chain. So we don't have to worry about this third argument. Perfect. We have all the information we need to combine these signatures. Let's go ahead and do that. We'll run E1 CLI combine block SIGs. What we need is first this block hex. Let me copy and paste that in. And then we need this list. We'll put that into quotes. So we need this list of pub key SIG pairs. So I have this list here. Let me first copy the one from E1. I'll just copy this and paste it in. And I will do the same for the second one we got from E2. And all I need to do is run this. And look what we get. We get this output. We see two fields here. One is a hex, which is the signed block hex. And the second one is this Boolean field, complete, which is set to true. If this is set to false on your screen, if you're following along and trying to learn how to sign blocks yourself, make sure to go back to the beginning of this tutorial and double check that con_max_block_sig_size parameter, which I showed you in the elements.conf file on each node. That needs to be set high, otherwise the signature will not be accepted. I digress. Now we have this big signed hex. All that remains is to try submitting it. So previously, if you recall, we tried to submit the unsigned hex and we got this error, block proof invalid. So let's submit the signed hex, which I have copied to my clipboard. So E1 CLI submit block, and I will just paste in that signed hex. And wow, look, we have no error. Let's confirm that this was actually added to the chain on each node by running the get block count RPC. We can do E1 CLI get block count. And look, E1 says that the chain now has one block inside of it. And E2 says the exact same thing. You can see that both E1 and E2 have accepted this block as valid and added it to the tip of their local copies of the blockchain. To summarize the process, in this section we have done quite a few things. We've proposed a block, had each node sign it, we've combined the signatures, we've checked that the signatures are valid and meet the chain's redeem script threshold. We've submitted this block to Elements, and then each node on the network validated this block and added it to their local copy of the blockchain. So now we understand how a federation can go ahead and create and sign blocks and add them to a chain. Awesome. I'll see you guys in the next section.